Why does looping beat indexing here? A few years ago, someone posted on active state recipes for comparison purposes, 3 Python/numpy functions. Each of these accepted the same arguments and returned the same result, a distance matrix. 2 of these were taken from published sources. They are both, or they appear to me to be, idiomatic numpy code. The repetitive calculations required to create a distance matrix are driven by numpy's elegant index syntax. Here's one of them. The third created the distance matrix using a single loop, which, obviously, is a lot of looping given that a distance matrix of just 1002 points has 1 million entries. At first glance this function looked to me like the code I used to write when I was learning numpy, and I would write numpy code by first writing Python code and then translating it, line by line. Several months after the active state post, results of performance tests comparing the 3 were posted, and discussed in a thread on the numpy mailing list. The function with the loop in fact significantly outperformed the other 2. One participant in the thread, Kia Meal, offered a reason why this might be true. The reason that I suspect this will be faster is that it has better locality, completely finishing a computation on a relatively small working set before moving on to the next one. The one-liners have to pull the potentially large MXN array into the processor repeatedly. By this poster's own account, his remark is only a suspicion, and it doesn't appear that it was discussed any further. Any other thoughts about how to account for these results? In particular, is there a useful rule regarding when to loop and when to index that can be extracted from this example as guidance in writing numpy code? For those not familiar with numpy, or who haven't looked at the code, this comparison is not based on an edge case. It certainly wouldn't be that interesting to me if it were. Instead, this comparison involves a function that performs a common task in matrix computation, i.e., creating a result array given 2 antecedents. Moreover, each function is in turn comprised of among the most common numpy built-ins.
TL. Doctor, the second code above is only looping over the number of dimensions of the points, 3 times through the for loop for 3D points, so the looping isn't much there. The real speed up in the second code above is that it better harnesses the power of numpy to avoid creating some extra matrices when finding the differences between points. This reduces memory use and computational effort. Longer explanation. I think that the Gauss distance matrix fast Euclidean 2 function is deceiving you with its loop perhaps. It is only looping over the number of dimensions of the points. For 1D points, the loop only executes once, for 2D twice, and for 3D, thrice. This is really not much looping at all. Let's analyze the code a little bit to see why the one is faster than the other. Gauss distance matrix fast Euclidean I will call fast 1 and Gauss distance matrix fast Euclidean 2 will be fast 2. Fast1 is based on the MATLAB way of doing things as is evidenced by the reapmap function. The reapmap function creates an array in this case that is just the original data repeated over and over again. However, if you look at the code for the function, it is very inefficient. It uses many numpy functions, 3 reshapes and 2 repeats, to do this. The repeat function is also used to create an array that contains the original data with each data item repeated many times. If our input data is 1, 2, 3, then we are subtracting 1, 2, 3, 1, 2, 3, 1, 2, 3 from 1, 1, 1, 2, 2, 2, 3, 3, 3. NumPy has had to create a lot of extra matrices in between running NumPy C code, which could have been avoided. Fast2 uses more of NumPy's heavy lifting without creating as many matrices between NumPy calls. Fast2 loops through each dimension of the points, does the subtraction and keeps a running total of the squared differences between each dimension. Only at the end is the square root done. So far, this may not sound quite as efficient as Fast1, but Fast2 avoids doing the reapmat stuff by using NumPy's indexing. Let's look at the 1D case for simplicity. Fast2 makes a 1D array of the data and subtracts it from a 2D and x1 array of the data. This creates the difference matrix between each point and all of the other points without having to use reapmat and repeat, and thereby bypasses creating a lot of extra arrays. This is where the real speed difference lies, in my opinion. Fast1 creates a lot of extra in between matrices, and they are created expensively computationally to find the differences between points, while Fast2 better harnesses the power of NumPy to avoid these. By the way, here is a little bit faster version of Fast2. The difference is that we are no longer creating delta as a zeros matrix.
Dis for fun. Dis.discalc distance matrix fast Euclidean. Dis.discalc distance matrix fast Euclidean 2. I'm not an expert on dis, but it seems like you would have to look more at the functions that the first is calling to know why they take a while. There is a performance profiler tool with Python as well, Profile.
If you want to see more, please consider subscribing.